Hi, here we are discussing refraction at a rare medium. This is an interesting topic related to refraction at a denser medium, the first topic. Here we do not derive this equation because we already done this one. So we just point out a few things regarding this diagram and regarding this topic. So here v2 is greater than v1, so we can say angle of refraction is greater than angle of incidence. So if we derive this equation, we get n1 sin I. If we follow the same procedure, we get n1 sin I is equal to n2 sin r. Here sin IC, when we consider I is equal to IC, then sin r is equal to 1, where r is equal to 90 degree. So we get sin IC is equal to n2 by n1. Here IC means critical angle. Critical angle, the relation is between critical angle and refractive index is sin IC is equal to n2 by n1. The same equation we got. So here what we are doing is for greater for angle of incidence greater than IC, we can write we can say that there is no refracted ray in this regard. So depending on the diagram, we can say that here incident ray is forwarding in the first medium like AB, and in the second medium it is AC. So when we consider the wave front, we can say that AB is the part we need and EC is the part we have to draw. Here it is not refraction, it is actually a reflection. That is a mistake. It is actually reflection of a plane wave by a plane surface. Here we are considering a plane wave front AB that is falling on the mirror, but at A it is getting reflected to the reflected ray, and at B it is just passing through the same medium to the point C with a velocity v2. So we can say that B to C takes a time to travel this distance with velocity v. So we consider from A it takes v2 velocity because of the same medium. So we can draw a v2 circle from the pointing at the center A, and we can draw AE distance, AE reflected ray. So we can say that AE is the same distance traveled from B to C, that is V2. So A is V2 and BC is V2. So we can say that this side is same, and we can say that the angle at E and the angle at B is 90 degrees. So we can say that these are all congruent triangles. So we can prove that I is equal to R, that is nothing but loss of reflection. So we can easily prove that loss of reflection is valid in this point. And the next one, we can extend this idea to any plane surface, any surface. So first we consider a plane wavefront that is incidenting on a prism. So what happens and it at this point means just imagine two plane wavefronts are there, two parts of the plane wavefront are there. So first part, the top part traveling less in the glass medium, and the lower part is traveling more in the glass medium. So we can say that in the second medium it takes much time, more time, because in the second medium velocity is less in the glass prism. So lower part travels less distance in the given time. So we can say that plane wavefront is a little tilt because the upper part moves faster and the lower part is moving in a slower manner. Similarly, through a convex lens, you can say that the upper and lower part of the plane wave is traveling less in the second medium. So it is having a slow pace, and the other part it is in air medium, so it travels in a faster manner. and the thicker part, the greatest thickness part, you can say at the center, it is getting slower due to the speed of the light in that medium. So we can say that it is actually a spherical wave that is converging to a point F, that is the wavefront we got. Similarly, you can say that a plane wavefront incident on a concave mirror having the same idea of getting reflection on this surface. You know that lower and upper part get easily reflected, because there you can see it will reach the mirror so fast, so it will just converge to a point, and the middle center point, it takes more time to reach the center part, so it will not diverge or this. So you can say that there is no divergence at the center, so it just seems to be a spherical surface. So it will converge to the point F, focal point F. So this idea of reflection or refraction, whatever it is, can be applied to any material that is our point of relevance to understand the phenomenon using wave optics.